All right, so good morning for the last day. Glad to have the first slot, so can catch you with a fresh mind today. To continue with actually, as I said now many times, I think most important part. Today I want to really go about this, you heard a few times now, these DMRG ideas and the so-called matrix product states. And the idea is kind of to really show you that everything we did so far was just doing just normal evolution of like some state vectors in exact regimes. But today I will show you really how to go beyond and treat systems of like hundreds of spins, if you like, exactly, in some cases. Okay, so as always, let me review what we did last time to put it into perspective. So last time really I just discussed how to really construct first sort of in a practical way some Hamiltonian using these sparse matrices, using just some Kronecker products. And then we looked, the example application was this type of long-range interacting spin model physics, where you have sort of competition between sort of short-range nearest neighbor spin physics and then these long-range terms. And we found a very good method to do this was this type of Krylov space method to just evolve a state vector from a time to a later time. It's a very nice approach, so you always construct your own space on which you solve the problem starting from an initial state using the powers of the matrix your evolution matrix that you want to apply. And then the second half I had discussed really open system dynamics, so Lindblad master equations. So now in the last Tony Chin lectures you learned much more about this, and I showed you how to simulate this. So either again doing some type of vectorization of the density matrix or doing this unraveling into trajectories. And I want to come back to this a little bit at the very end when I want to show you some recent results and some recent outcomes. So this brings me for the plan of today. So really today I want to show you a strategy to go to systems way beyond 30 qubits, if you like, using these matrix product states. So the plan is I need to have first some kind of preliminaries. This is going to be quite short, but I want to introduce the concept of the so-called Suzuki-Trotter decomposition. And then the most important part is probably here. I'm going to talk about the really fundamental idea of how to compress quantum states. And I'll just introduce bipartite entanglement entropies and the singular value decomposition as really the key concept of all of these DMRG MPS methods. Then I want to introduce these matrix product states. And sort of the way, I mean, what you can think about, like you hear words like DMRG. So DMRG is an algorithm that kind of makes use of matrix product states. And there are many different algorithms that you can write down to evolve or manipulate matrix product state in some particular way. I want to just introduce one algorithm, which is called the time evolving block decimation algorithm, or TEBD, just because it's really, on the one hand, it's really the simplest one, the simplest way to update a matrix product state. And with this one can actually, in principle, do everything. It's not the most efficient way of doing everything, but it's kind of a very nice method to get the idea across. And then at the very end, I want to discuss of how to apply this in some recent work to some recent type of problems. In particular, coming back to the dreaded question about the Gauss-Peteevsky equation and if it's valid or not. Okay, but just to start with, so again, the motivation, the problem is just, let's for now stick to pure state evolution with a time-independent Hamiltonian, so I want to compute this thing here. Right, that was what we were all talking about, just building the matrix exponential. And what I want to talk here, this Trotter decomposition, is just another way to make this matrix exponential of a Hamiltonian a little bit easier. And in particular, I consider here only Hamiltonians that have sort of few-body terms, in particular here only really pairwise terms. And pretty much all of the Hamiltonians that were discussed here, they just fit into this class. So you have some type of many-body systems, you have sites I and j, and you have some two-body terms coupling them. And you have some local terms and fields, which you can also actually absorb into these two-body terms, if you like. So this is a very generic thing. For example, if you have just particles hopping between nearest neighbors in 1D, bosons, then it would be a term like this. And then, of course, you would only have not all of the I larger j terms, but really only the nearest neighbor terms. And just one little comment here, because quite often one hears that this MPS, DMRG, only applies to one-dimensional systems. And just to be clear, in principle, one can use everything I say here also for higher dimensional systems. It's just really, if you try to simulate these higher dimensional systems, then it gets really computationally much more complicated. And I want to show you later why this is the case and why in 1D it's actually the most nicest way in such a way. But in principle, one can totally do this. So even if I have a 3D system, I can just start labeling my individual sites in some order that I like, that of course can be optimal for one system or another. And then I want to just say, okay, these two-body terms, so that's what I did here. And then if you have sort of some long-range terms, say between like here some spin 12 and some 29, then of course you have effectively, if you rewrite this thing as a one-dimensional chain, then you get some kind of long-range terms in the system. But fundamentally, I always want to think about it because this MPS concept itself is sort of one-dimensional. That's why I want to also kind of write a linear way of my systems. But one can, in principle, always do this. If I have this type of long-range terms, the easiest thing I could do, I can introduce some swap operator. So I can just change the ordering of these. I can just change the states here, but then have an interaction there, and then just change it back. That would be one trivial way of do like long-range gates. Of course, there are better gates. Okay. So what is this Suzuki-Trotter decomposition about? It's actually a really extremely simple concept. Of course, as always, what we want to do is we want to do like a stroboscopic time evolution, so we have a small time step. And here I want to consider a time step which is essentially smaller than the norm of these two-body terms that I look at. Right? So typically, if I'm hopping, I set my J parameter to 1, then this in practice means that my time step should be again smaller than the inverse hopping amplitude in the system. And then the simplification of this Trotter decomposition is just that I say I have my full matrix exponential with this Hamiltonian that all has these two-body terms here. And I just want to write it as like instead this product I over J with all these two-body time evolution on individual terms. Right, and of course if I do this, I make like some type of error. Right, and the error you simply know, for example, from this Zassenhaus or all of these Baker-Campbell-Hausdorff formulas. If I have a matrix exponential of two matrices with some prefactor, I can approximately write this E alpha x, E alpha y. And then I have some term here that depends on the one hand on the commutator between those two matrices. And on the other hand, of course, on this parameter alpha. And then I have higher order terms here. But you see, if I make this term, this time step that is my prefactor alpha, if I just make it very small, I can just approximate an exponential of the sum by the product of the terms. That's the idea. And if I do that, that would already be sort of the lowest order Suzuki-Trotter decomposition. Of course, I will show next step like higher order decompositions. Nobody would use this first order thing, but just to understand the main concept. And the idea that we're going to have is now, if we do this, this is very useful for this MPS concept because now we can kind of have little gates, little time evolution operators between just the pairs of my spins, for example, that I have in the system. Okay, and this is, for example, just to point this out. I mean, this Trotter decomposition became really known very well when these digital quantum simulation ideas came about. When, in like '96 here in this paper, when they had the first time saying, okay, what if I have a quantum computer? If I have gates, then I have to write my time evolution of a quantum system in terms of gates, and that's exactly the same thing that I'm doing here. Okay, so of course, in practice, as I said before, one would not use just the product of the terms. That would make a huge time step error. In practice, one uses some higher order decomposition. And there's actually a really beautiful paper out there. It's from '99. This sort of has a paper where they worked out all of the algebra of all of these high order decompositions, and it's really magic. One can just use sort of some formulas on this paper, and it works beautifully. But just to introduce the main concept, here I just give a simple example of what would be a second order method. Imagine I have some type of Hamiltonian where I have sort of just 3 sites in my system. And let's say I have a Hamiltonian that couples 1, 2, 2, 3, and 1, 3. Then I can do the following. I say, okay, I introduce half the time step. And then I start by applying sort of the time evolution for the Hamiltonian 1, 2. Then I go with 2, 3. Then I go with 1, 3. Whatever order I choose. And then I just reverse the ordering, and I go again with 1, 3, 2, 3, and 1, 2. So here I have this sweep here that one can call U delta t over 2. This is like a unitary. And then I just do a U dagger of minus the time step here. So I just apply each of the gates twice. And then one can show, if one works out really this Baker-Campbell-Hausdorff stuff, that here the error that I make is only the time step to the power of 3. So again, this is something that really pays off, because if I would use this first order, I would have just like 3 sweeps here, but I would have an error which would be delta t squared, and here I have an error that goes delta t3 only by doubling the number of sweeps. And what this paper has, it has sort of all of this type of sweeping type of Trotter decompositions worked out. For example, there's a fourth order decomposition. Of course, if I would write it down here, it would take the whole slide. But there one needs sort of 18 of these sweeps with different time steps, with time step over 6, time step over 12, and it looks completely random. And then if you implement this, you see that the error is of order time step to the power of 5. So this is really cool. And I think this fourth order method is, again, the standard way to use. Good, so that's it from this first part. I really wanted to introduce how you can, if you have a big many-body system with 2-body terms, Trotter decomposition helps you to break this down into little time evolution on sort of pairs that act on your Hamiltonian. Good, but this is going to be now definitely the most important part. It really brings the main idea across. So I want to introduce concepts about bipartite entanglement and singular value decompositions and how they are connected. So again, it's going to be very simple, so just let me define what I mean by bipartite entanglement. So I talk about bipartite entanglement entropies here, which is, I think, one of the few very well-defined entanglement measures out there. And the concept is really incredibly simple. Let's say you have a state on some type of many-body system. And let's say we just split the system into 2 blocks. The one block I call block A, the other one I call block B. Then simply by the definition of what entanglement means is that I have to, in the case that I can write my total state, which has to be a pure state, if I cannot write the state as like the product state on A times the product state on B, then I call those 2 blocks entangled with each other. Right? So this is not mean field. In the mean field approximation, I made this product state assumption. Here I say my state cannot be written in this way. So the question is, how can I sort of quantify how much of this entanglement is in the system? And the concept behind this entanglement entropies is that I just look at the state in my system A or the state in my system B by just tracing over the other part. So this is really, if I give you an experiment, I give you the block A, you get this state, and it's going to be described by this reduced density matrix A. And then, of course, if the total state is actually in a product state, something like this, right, then you see immediately that the state that you get in A or in B, they're going to be pure states. Right? So this implies a pure state. If I give you the like the sub-block of the system A, and it's pure, then you really have all of the information of the state that you need is in your subsystem, right? So there's nothing in the correlations between the blocks. However, if there is some entanglement between them, then of course it's going to be a mixed density matrix. Just to show this very quickly, let's take just a system of where we have 2 qubits which are in a maximally entangled Bell state. So let's take a state like 0, 0 plus 1, 1. Right, if I now compute my reduced subsystem density matrix, let's say on block A, right, so I have to trace over the system B, so I have to do this sum here with the 0 on B and the 1 on B. But here in this psi, I get all these cross terms. I have the 0, 0 term, I have the 1, 1 term, then I have these cross terms, but these cross terms, they're going to go away, because if I trace out the system B, then of course here I have 0 and 1, and this is going to be off diagonal, so it's not going to give me anything. And in the end, I end up with a reduced system density matrix that looks like this. And this is a maximally mixed state, right? So this is really a pure statistical mixture of like classical states. So with 1/2 probability, you find the particle up, and with 1/2 you find it down, but really in a purely classical statistical mixture. So this state is going to be maximally mixed, and the fact that it's mixed is going to tell you that there is some entanglement with the system B. And the idea of an entanglement entropy is just to really compute the entropy of this reduced subsystem density matrix, which is going to tell you how much of information you lost because of the correlations with the system B. Of course, always assuming that the state psi is actually a pure state. Okay, so said what we need to do, and that's why it's called entanglement entropy, is I just compute the entropy of the reduced density matrix, and one can use several entropies there. Most commonly, one uses the von Neumann entropy, and then one calls this thing the von Neumann entanglement entropy. And so I take my system matrix and the subsystem rho A, and I compute this thing minus trace rho A log rho A. I always use the basis 2, which for spin models is really the most natural thing to do. You will see in a minute why. And then, of course, what this thing means is here this trace of the matrix with the logarithm. Of course, I mean, I just do this with the eigenvalues of this reduced density matrix. So here I introduced the lambda alpha, which I call the eigenvalues of the reduced density matrix. And so they're going to give a probability distribution, right, because trace 1. And from this probability distribution, which is given by the eigenvalues of the reduced density matrix, I compute the entropy. And if the total system is a pure state, one can easily show that if I compute it for subsystem A and subsystem B, it's going to be the same. So in a way, it's really the entropy. It's sort of lack of information. It's like if I give you one part of the system, how much information do you miss to construct the whole state? And this is how much entanglement there is with the other part. Good. So now one can ask, okay, so what this number, this entanglement entropy, so what can it be? You know, I have this simple example of the 2-qubit system, but of course we want to treat large states of like many spins. So we have big subblocks. So let's say that we have a state, and we have some subblock, block A that has some dimension dA. This is the Hilbert space dimension of this part, and then I have another one, block B, which I can make larger if I like. And I just wrote down again the definition of this phenomenon, entanglement entropy. But now, of course, here I have all of the eigenvalues of the reduced density matrix of a big subblock in the system. So if I have this dimension dA here, then of course, again, if I have the kind of the no entanglement state in this, like when I had like a product state, this would be here a probability distribution where I have one eigenvalue, lambda alpha, being 1 and all the other ones being 0. Right? This is really when you have your reduced state is fully described. You don't have any uncertainty about it. You just have one eigenvalue of your density matrix. So in that case, the entanglement would be, the phenomenon entanglement entropy would be 0. On the other hand, now I can have different type of distributions here of these eigenvalues. And sort of I can think about what's the worst case. Well, the worst case is really the totally mixed density matrix in the system. Right? If I have like the maximum lack of information, I have a diagonal density matrix where now all of the elements of my diagonal density matrix are going to be 1 over the dimension of this subblock, block A. And then if you compute this, you get a sort of 1 over the A, log 2, 1 over the A, and you will see that this is going to be just the logarithm of this dimension. Right? So fundamentally, this phenomenon entropy is really a quantity that goes somewhere between no entanglement when it's 0 to maximally the logarithm of the dimension of the Hilbert space that you have in this block. Again, going back to our 2-qubit examples, if I take a product state, let's say 0 and 1, and my reduced density matrix was 1, 0, right, then I have this situation where one eigenvalue, I mean, this is already a diagonal density matrix, so one eigenvalue is 1, the other one is 0, then my entropy is going to be -1 log 2, 1, it's going to be 0. Whereas here I get 2 times the same value, so I get -2 times 1/2 the logarithm of 2 of 1/2, so I get 1. Right, so that's why I like the logarithm base 2, because it's sort of here, for spin models, it's a natural thing. If I have one spin, it goes between 0 and 1. If I have 2 spins, then it can go between 0 and 2, and so on. All right, so far only the just theoretical concept. So how would I compute such a thing in practice? So if I want to have a many-body state, I need now these eigenvalues of my reduced density matrix. So how would I get it? And this is really where the singular value decomposition comes in, or also Schmidt decomposition. So I want to focus now for a minute on let's just say like we split our system right in the middle. Let's say we have an even number of spins, and let's say that my left dimension is A, the A, the right the B, and let's say they're both the same and they're D. So what one can do is now if I take this state and I can just write it down, somehow I find some type of eigenstates on my basis A, not eigenstates, some type of basis states on A and some types of basis states B. I call them here IA and JB. And I just can write down my state in this form with these coefficients just defined in some basis for the whole Hilbert space of A and the whole Hilbert space of B. And then what one can do is one can now do the singular value decomposition of this coefficient matrix. So singular value decomposition, I don't want to go into too much details, but this is something of a general matrix one can always do. it essentially means I have some matrix here, I call it C, and I just write it as some some product between three matrices, a unitary matrix U and a unitary matrix V, and then there's this real diagonal matrix S over there. Right, so in the coefficient, in the element-wise notation, it's written like this. And in the middle, I have this diagonal matrix, this S alpha alpha, and the elements, they are positive, and they are called the singular values of the matrix. Right, so you see already in some way, if you do this, you have this matrix C, then here, with this unitary, you kind of define a new basis to the left side, and with this V dagger, you define a new orthogonal basis to the right side, and just this S are just really the coefficients of the state in this new basis. Right, so, and a simple exercise you can do is now, if you compute now, if you do this, if you write now, if you insert this here, you write your state in this diagonal form, so you have a diagonal way that you write it sort of in such a way that you have the same, only a diagonal elements in this coefficient here. Then if you trace over the subsystem B, you will see that you reduced subsystem density matrix rho A just can be written as a sum over the singular value squared times this new basis, where this new basis is defined by these matrices U. Right, so that's the main concept. So now a way to think about this, if you take the total state, you write it down for the splitting that you want, and if you do a singular value decomposition of these coefficients here, then the singular value squared are going to be the eigenvalues of the reduced density operator if I trace over one part. Right, so really what I have to do is the things that I called lambda alpha before, that were this probability distribution, they're really just these singular values squared. So if I have the singular value squared, I can now easily compute the von Neumann entropy of this, just same formula as before, just with S alpha alpha squared. Okay, so you may already see where this is kind of going. So now we have the following. We had our splitting of our state. So we had our total state defined in this form. We did the SVD, and we now have the entanglement entropy of this arbitrary state that we put in. Okay, now really the fundamental idea that I want to introduce here is that if you now look at this for like typical states, again, this S alpha alpha squared, they normalize to 1. They are a probability distribution. So they're going to have some type of distribution. That, I can order them in the put the largest singular values first, and then I order them in descending order. And then typically they will follow some distribution. Right, so the fundamental idea of this kind of compressing a state that I want to introduce is that at one point one says one introduces here this number, this cutoff number chi, and then one says I'm just going to ignore all of the contributions of the singular values which are larger than this chi. Right, so in the formula for this von Neumann entropy that I derived here, this means that for the full exact state I would have to compute it with all of the eigenvalues, so I sum over the whole Hilbert space here. But instead now here I just discard all of the singular values below a certain threshold. And then instead I just say, okay, now of course I have only a sum here that goes up to chi. And then what this implicitly means is that my von Neumann entropy is now going to be limited by the logarithm of this value chi. Right, so you see fundamentally in the many-body system, this entropy is limited by the logarithm of the Hilbert space size of your subsystem, but now I artificially set an upper bound to this. And of course, the error that I'm doing by this is given by like the sum over all of the singular values squared that I cut away, because then of course afterwards my state is only going to be approximately normalized up to some loss of the norm that I have defined here. Good, so this is where I come to the chicken finally, in case you wondered. So this is just to introduce the concept. I always show this with some example image. And typically, wherever I do, I just try to take a local picture. And I thought the cat running around here, I was always super happy because I always take usually cats as example pictures, but then I didn't see the cat again, and there was this, I think some of you have also seen it. It was confirmed. It's just to prove that the chicken was running around out over there. So I took this picture of this chicken. I made it like a grayscale picture. Right, and a grayscale picture is just meaning like each of these pixels here, it's going to be a value between sort of 0 and 256, so I can renormalize this. So each, I can think about this really just as each pixel being some element of a matrix. Right, so then you could sort of define like a state where I take this coefficient matrix here, psi ij, being defined on this bipartite Hilbert space, just I take this picture as an example. Right, so the Hilbert space dimension is the number of rows and the number of columns that I have here in this picture. And then what can I do just for fun? I just take this picture, I load it into the algorithm, I then do like a singular value decomposition of this, and I get some distribution of the singular values. And then I just here, then afterwards, I just do this truncation that I just introduced. So I cut away all the singular values below a certain value, and then I just reconstruct the matrix, and I see how the picture looks like. And here you see if I really only take the first singular value, this is really only take the largest one. So this is kind of your mean field chicken, where you make a product state assumption. Then you reconstruct the picture, and all of the information is gone. It's really completely lost. Right? So you cannot see anything, well, maybe a little bit of the color distribution. But then the important thing is if I now go to something like where I only keep sort of 5% of the total values here, and then I reconstruct the picture, and I get pretty much all of the information that I want back. Of course, there's a lot of fine structure here that looks kind of messed up, but it's like in a quantum state, you know, some of the fine details are maybe not so important. You just are interested in the most relevant information. You know, maybe you would just want to identify it's a chicken here. And then just a few number of these singular values are actually enough. So this is if I would only take a slightly entangled chicken in a way I only keep states where there's sort of really a little bit of entanglement in it. But like one fun fact is actually, this is actually a pretty hard picture. Like usually one gets away with 1 or 2%. For this chicken I needed 5%. There's a surprising amount of structure in that picture. I guess it's because of all of this background here. Because actually, like another fun fact is like the picture that is worst possible to actually compress would be one where you just put completely white noise. But if you would try to compress this and reconstruct it, then the new white noise that would come out would be completely different than the old one. But of course, then white noise also has nothing interesting in it. And that's really the idea. You can think about this as an image compression technique for your quantum state, because your quantum state has some structure in general. And you just exploit the fact that it has some structure to compress it, to write it in a smarter way. Also, singular value decomposition was used for early image compression, but it's not ideal for images. All right, good, and that's the most important concept. If you understand that, then I think you will have relatively easy time to understand what an MPS is. All right, so matrix product state. You will understand what this word means later. So, but just to introduce it, I'm sure many of you have actually seen this already. I just want to introduce a little notation here, which on first sight looks kind of rather complicated, but it's actually really super simple. I mean, this is nothing complex. It's just really, I have these things that I have to deal with: numbers, vectors, matrices, and higher dimensional tensors. And of course, it gets annoying to write down all of these things in like the element-wise description. So I just want to have an easy diagrammatic way of just writing down operations of matrices or tensors. So what I just say is, if I have this object over here that has just this blob here, this is just going to be in general some complex number. Let's call it C. If I take the object and I put a little thing, a little line out there, I say this is D1, then what I mean by this is that this thing has one index where this I runs up to mention from 1 to D1. So this is going to be a vector. On the other hand, of course, if I have two lines coming out, I have just in general two indices. So this thing is going to describe a matrix. If I have 3, then I have a 3-dimensional tensor, and so on and so forth. And that way I can write down sort of all these high-dimensional tensors that I'm going to need. And just avoids writing down sort of messy type of sums. And it's also nice because, as I show here in this example, it will tell you sort of something about the numerical complexity of tensor operations. So very simple examples. If I take, for example, this object here, which has one index, let's call it D1, and I just add this object here. So, and then if I connect these two indices, what I mean is by connecting them, I want to just do call it the contraction over here. So you just sum over this index here, this goes away. So by this I mean really here the matrix vector product. Here I sum over this index D1, so I have my vector has this index I, the matrix has index I and j, I sum over I end up with a vector j. So this is really a matrix vector product. If I get rid of this index, I come out with a vector. Right, and now if you want to ask how on a computer, how expensive is such an operation, well, you just count the number of dimensions which are involved here. So here I have to sum over this, and I have to have one thing coming out. So you count those up. So you see this is of order D1, D2 operations, because for each element j, I have to multiply these I elements here. And the same is true then for more complicated contractions. You will see a few examples later. A common thing is, for example, I have this three-dimensional tensor contraction. Let's say I have an index that I call here that goes up to dimension chi. I have another index chi here. I have an index d here and d here. This is sort of a contraction between this 3D tensor with a matrix. It gives me, again, a 3D tensor. And I can count here, this needs d squared chi to the power of 2 operation. So this is going to be the numerical cost of doing this operation. And also I can write, for example, the singular value decomposition that we're going to need. I can also write it in this very simple notation. Here I had the situation, I just start with a matrix C that is a D1 times D2 matrix. And then I just split it into these two matrices here and the diagonal matrix here in the middle. And this also typically has the cost of the minimum of the three products in here. So this is usually for all of the algorithms where the computational bottleneck should be. Yes.
How do I know that I sum over the row or on the column?
No, because I mean each index here, right? So I mean that's your choice, right? That's how you want to write down your matrix. But it doesn't really matter which way you write it down. You just, you name your indices. Right? If I write it as like a matrix and I think about column and row, then I have to order my indices. Right? And I just say that my index 1 here, this for example, would be the row index. And I remember that this is in the row. So this is the first index. And then the second index would be sort of my column index. I say this is always the second index. But that's purely my choice. If I change the ordering, I just have to reorder my matrix, how I store it. Right? So it's kind of really free here. This is actually a good point because this brings me to this next slide. And this is actually exactly the only kind of code piece I want to really show today. But I mean, there are many useful of these tensor libraries out there. So there's a lot of toolboxes that help you do these tensor constructions in an elegant way. One of the most popular ones is this. It's called iTensor. It's available for Julia and C++. And what is done in this toolbox is actually super nice because there, it's exactly the point. You don't have to worry about how you order your indices because usually you have these three-dimensional tensors. Then you have to remember where your dimension is in your tensor. Then you have to permute dimensions and do things like that. Here they take a different approach. What you can do in this type of toolboxes, you can define first the indices as a type of object. Right? So I have, for example, here this tensor matrix construction. I have this three-dimensional tensor a matrix B, and I want to get this tensor C. The way that one can do it, one can define these indices. I have a left chi, a right chi, I have an upper and a lower index. And then I define my tensors from these indices. And then I can just do something like this, and then you will contract over the indices, which are both the same indices in the thing. And that helps a lot to write this type of codes that I will introduce later. Okay, I said there's many of these tensor libraries out there. Actually, one of the coolest thing here, this is just like a little side remark. What's very annoying in these algorithms that I want to introduce is to introduce conservation laws. So I had, for example, this example of the Bose-Hubbard model where I have a fixed number of particles. And of course, if I have now this state decomposition that I'm going to introduce, it's going to be kind of annoying if you want to keep track about, like in your local tensors, where are which blocks for particle numbers. And it's a very elegant way of just introducing number conservation in these type of constructions. The way one does this, one has this type of tensors where one has sort of input flow of quantum numbers and output flow. And then one can show that sort of contractions only work when input and output is matching. And this is a very elegant way of doing that. And this is also built in this library here. Okay, if you didn't understand what I was saying, don't worry, it's not important. It's just a little detail. Okay, so, but now importantly, so what is this mysterious matrix product state? So now with this diagrammatic notation, I can just very easily introduce the concept of it. So let's take again our many-body system, whatever it may be, for example, spins. And then, before we had this construction where we had like the Kronecker product between the matrices on different sides. And that's one way of doing it, but I can also just think about this state vector that I have. I can just think about it as this sort of m-dimensional tensor. So I say I have here a system where I have m sides. Each local dimension has a small dimension d, so for spins this would be 2. And then I can just write my many-body state as this, this m-dimensional tensor where I have C, I1, I2, up to IM. This is just regrouping your big state vector into sort of one object. Now, if I use the diagrammatic notation, has this m little indices coming out. Right? One can always regroup indices, it's not a big deal. Okay, and the idea of a matrix product state is really that I take this monster here and I write it into this form here. And of course, the way that I've written it here with the little blobs, it looks already familiar as this singular value decomposition concept. So I would take, for example, this thing here, right? And I said what I just said before. You can always go from this tensor to like a state vector. So think about that. You just split out the first side here, so the first qubit, for example. You split it out over there. Then you have all this m-1 indices left, and you can combine it into one index. And then, well, this is just, this is just going to be a d times 2 to the m-1 matrix. And of that matrix, I can do a singular value decomposition. Okay, so I do a singular value decomposition, so I get my left unitary matrix U, I get my singular value diagonal matrix here, and I get the other monster matrix here. And then I can just, doing this, I just take the next part out, and I do again the same thing, the same singular value decomposition. And that way, I just move from the left side to the end, or I could do it from the other side too, and I construct sort of this type of thing in this particular form. This is just a theoretical concept. In practice, one actually never does this, but it's just to understand what this MPS is. Okay, so just some remarks here. In most of the literature here, I wrote it in such a way that I kept this matrix product state, so this I call a matrix product state. I kept explicitly this singular values here as these diagonal matrices. Most common in the literature is actually to absorb these matrices into these three-dimensional tensors. Right? This is, I can always do this. I can take this matrix, multiply it into there, and then it looks cleaner. But then sort of you have to kind of remember where you multiplied these matrices in. Because if I do it like this, then as I said before, singular value decomposition tells that there's sort of a good orthogonal matrix, so a good orthogonal basis to the left and the right of this singular value. But if you multiply this in, you kind of destroy one of them. And then people kind of write it in such a way that they remember just that the basis to the left or the right side is an orthogonal basis. This is called orthogonality center in the literature. But it's a technical detail. So I think conceptually it's often nicer to think about it with these explicit singular values. Okay, a second note is, so why is it called matrix product state? Maybe a confusing name, but it's really a completely different way to think about this object over there. Here I have this three-dimensional tensors here, but you can also think about it as a matrix product. So let's write a state in such a way that my particle for the first side is described here by this first object. So this is really, this has two indices, but I can write it as a vector where the elements of the vector are local vectors. Right, so here, these objects here are really the local states of the system. So they're like local cats. So I write down like here the first side as a vector where the elements of the vector are these local cats. And then for the second side, I write now here I have three indices. So I have a left index and a right index. These are my column and row indices of this matrix here. But now the elements of these matrices are also little vectors. Right, so instead of thinking about these guys here in the middle as sort of three-dimensional tensors, I can also think about them as being a matrix with elements of the matrix being actual states. And that's the origin of the name matrix product state. Because you can think about it as a generalization of a product state. Because you can see already what happens now if I set this dimension here in between, if I set it to 1, if I only allow one state, then this would all be 1 by 1 matrices, and then I get again a product state. So this is really a generalization of what a product state is to states that can feature some entanglement, as I will show next. Yeah, this is actually just what I wanted to say. I said right now. So again, here, this is what I call the matrix product state. I have some finite dimension here between my sides. But let's say if I say set all of these horizontal dimensions here to 1, right? Then I have really states with 1 by 1 matrices, and then I can write it like this. And that would mean, again, I just have number times number times number. So then it would be, again, a product state that's then, again, very similar to what you would do in your mean field approximation. And then you exclude any type of entanglement in the system. But it's really, the product state is a special case of our class of matrix product states. Good. And so you probably already really guessed by now, but really the key thing is that really now the question about how large my local dimension between those things is. So how much numbers I need to on this index here, this is going to tell me how much of bipartite entanglement I can have in my full many-body state. Right, so for that, I write it again in this form over there. So this is a simple example. Let's just label it in some way. So let's call these dimensions here. Let's say that they have from these three-dimensional tensors here, this right dimension of this one and the left of this one is limited by a number that I call chi3, or in general, chi I plus 1. So if I split my system into a block A, where I have all the sides from 1 to a side I, and then I have a block B, where I have all the sides I plus 2 up to M. Here, example is I equals 3. And now, of course, because I constructed my MPS using this singular value decompositions starting from one end, so now I have, but for a bipartition here, I have directly available my eigenvalues of the reduced density matrix for the block A. So in the end, here, if I have a value of chi I and I limit to some value, then it tells you that the entanglement across this side I, so between the whole block A and the whole block B, is limited by the logarithm of this bond dimension that I have here. Again, the scenario from before, if I set all of these bond dimensions, so this chi, I'm going to call them bond dimensions now. If I set all of them to 1, then really the entanglement entropy for all of the bipartitions that you can do in your system is going to be limited to 0, and you're going to restrict yourself to product states again. Is this clear so far? Good. So again, so as I said before, if I do this construction, I don't really win anything in the system. I mean, if I really just go from the left side and I do this consecutive singular value decomposition, I'm going to create this MPS in this particular form. And then, of course, I can ask now, if I do this for an arbitrary state fully exactly without doing any truncation, I can see how large these bond dimensions would need to be. Right, so here in the first part, I said if I split out only the first side, and then I have this d times 2 to the power d to the power m minus 1 matrix. If I do an SVD of this, the maximum number of singular values I can have is only d. Right, so it's mean if I start from one of the edges of the system, the maximum amount I can tangle this one spin with the rest is only going to be limited by a logarithm of 2. Right, so I only need a maximum of the local Hilbert space dimension for this bond dimension. But then for the next one, I'm going to need, of course, d squared, and then I need d3. And then the largest bond dimension I'm going to need is in the middle of the system. And there, my bond dimension, if I do everything exactly, it's going to have to be d to the power of m half. Right? So, and of course, this is still something that grows exponentially with the system size. Right? So if I wouldn't do this truncation in my system, then I wouldn't gain anything. I would just, in a complicated way, rewrite my original state vector. But now if I go back to my key idea and I introduce really this cutoff value chi for all of these indices there, then I strongly limited the amount of entanglement that I can have, but I need much smaller numbers to describe my state. Right, so if I have an MPS which has this bond dimension chi, then you can easily see the number of storage space that I need is going to be n times, it's going to be proportional to the number of sites that I have. sorry, this should be m, number of sides that I have times chi squared times d, because each of these three-dimensional tensors has something like chi squared d elements, and I need just n of these elements. And this is can be much, much lower than just 2 to the power m, of course. The price that I pay is I limit my entanglement to the logarithm of this cutoff value that I choose. Okay, and that's the main idea. Makes sense or overwhelming? Okay. Yes. This one?
Yeah, I just have to copy.
Okay. I will still, yeah. I still said I'm gonna send it, but if you like writing, okay, good. All right, so good. So I introduced the idea about what is this matrix product state. So, but of course I have not told you at all yet sort of how to update the state, how to actually do something with it. And this is now where I will introduce this so-called TEBD algorithm, or time evolving block decimation algorithm. Good. So this is really just bringing everything together. Now it comes back of what I had motivated in the very beginning. So I had already introduced this Suzuki-Trotzer decomposition, which means that all of my complicated matrix exponential that I want to apply, I just broke it down into these little two-side gate thingies. So if I write it now down in this diagrammatic MPS language, what I need to do is I'm going to have this, what I call sweeps. So I have these pairwise gates that I apply to my state. And now I want to apply them, and I bring them to this nearest neighbor form, introducing some swap gates if I need. And now I just apply these gates to my MPS. So what this means is I have my initial state, my state at times t. And now I have this whole train of these two-side gates acting on nearest neighbor that I want to use to update my state. So I have problems like I have this gate U. This here is really, it's a 4x4 matrix. Okay, I use spin language, right? So if I have like any type of gate involving two of the spins, I can have a 4x4 matrix. But I can also write it as these four-dimensional tensors where each dimension is 2. And then I have this thing, and I have to apply it to my MPS. I have to update these tensors I have here, and then I go to the next gate. So it's this consecutive going through, always piece by piece updating the state. And then I do this for all of these complicated sweeps that I had introduced for the Suzuki-Trotzer decomposition, and then I get my new state at a time plus delta t. Right, and that's how one does it actually also in practice. I mean, I introduced this singular value decomposition construction, but of course in practice you always start with a product state. You start with a simple state. We had many examples here, starting with the nail state, for example, yesterday, and this is a product state that you can easily write down exactly in this MPS form, and then you just use your type of evolution to introduce some type of entanglement in the system to create this type of bond dimensions, to grow them. Okay, and yeah, sounded very fancy TBD algorithm, but all that needs to be understood is really on this one slide here. So it's conceptually actually really super simple. Was introduced here in 2004. So what the TBD algorithm is, it's a terrible acronym, by the way. It's just people are not good with acronyms in this field. And what this says is essentially I have this problem here, so I just contract all of this into one into this object here. Right, so here one can now start playing around about what's the best order to actually contract these tensors with each other. I can start, for example, first putting this in that, and then putting this in that, and then putting this there, and so on. And one can show here that the optimal contraction scheme that you can come up with has a complexity of chi to the power 3 d squared. This is typically characteristic of all of these algorithms. They always grow with this bond dimension to the power of 3. Right, which is polynomial, so if you choose a finite number, it's still something that's relatively efficient. And then you have this object here, and the biggest problem here, of course, is that this thing is now not in the canonical matrix product state form, so here you have really now grouped this type of, you've entangled these two spins together. So what you have to do at this point, you have to do a singular value decomposition, right? So you bring this one back into the original form. And that's an intuitive way of how you see if you do some time evolution, how your system is going to induce entanglement in the system slowly, kind of gate by gate. It's always growing this bond dimension. Because if I do the SVD, my new dimension that I have in here, it's going to be the local dimension here times this bond dimension I had before. So in order for my MPS to not blow up to like a huge size, what I have to do at this step, of course, I have to do a truncation again. So one does this, and then at this point, one again truncates these indices here at this maximum value that I allow, chi, and then I throw away all of the other singular values that have the indices chi plus 1 up to d times chi. And this is the error that I have to, if I use this algorithm, in every little step of every Trotter cube decomposition, I have to control that this error remains really, really small. Right? That's actually the reason why in practice this TBD is not really the go-to method nowadays, because you make this error in every of these gate applications and you don't really know very well how big your error of your final state is. That's why there are much more elegant methods, I will mention them briefly later, where you update your state and you know the full error after a time step. But conceptually, this is really the easiest algorithm. Okay, so you see already the really condition that you need. If you say now, if you want to simulate your system, it really doesn't matter how large your system is going to be. But the crucial thing is really sort of how big do these horizontal dimensions of your MPS grow as a function of time. And as I motivated before already, I can just summarize this in this one number, which is the entanglement entropy. So the entanglement entropy is actually a crucial number that tells you how difficult it is to simulate something, and not necessarily the system size. So as long as this error stays small, then my simulation is going to be fully exact. I don't make any error. Which then, of course, led to this whole research field of asking, okay, how does this entanglement entropy really grow as a function of time? And just to show you how this goes in practice, this is some plot from some older work that we did. It's an example simulation for this Bose-Hubbard model that you heard now a few times. So I have here really these examples. I have my bosonic atoms trapped in this optical lattice. They can hop between the two different sides with this first term here, and then they interact strongly when they're sitting on the same side. And then experimentally, a popular thing to do was that initially you do this quench where you start, for example, in the Mott insulator state. So you prepare a state where you make the lattice very deep and you really pin down your atoms on individual sides. And then at a very short time scale, one makes this lattice very small, so that the bosons can actually start to tunnel through the lattice. And then in this plot here, what I show you is really the time evolution of the von Neumann entropy in a system of like 100 sites. The time evolution of the von Neumann entropy if I split my system right in the middle. So you see initially it does not start exactly at the value 0 because I started in an exact Mott insulator, which still has some little correlation. So it still has some small amount of entanglement, but I can really exactly write this as an MPS, so this is nice here. But then if I have like the time evolution, you see this entropy is growing linear as a function of time. Here the time scale again is given in units of the inverse hopping time here. And then what you see here is that here this number L that I introduced, so sorry, I forgot to, no, here I have it. So this is MPS simulations where this maximum cutoff value that I just introduced, I just limited it to 2 to the power of L, right? Because if I limit it to 2 to the power of L, so I go from 4, 16, 32, 64, and so on, then if I have L4, for example, then I limit the von Neumann entropy to the value of 4. So you see, if I now simulate everything with an MPS where I set this cutoff to 4, I start evolving my system fully exactly, and then at that point, things start to go wrong and my entropy levels off, simply because I cannot represent states that have larger amounts of this entropy. But then I go to L equals 5, I can simulate the system just a little bit longer, and then 6 and so on, up to 9, I can go to later and later times. And of course, this is one example where you now see, here I increase this parameter chi in my computation exponentially with L, but I only gain a linear amount of time, right? So you see if you have this type of volume law behavior, that your von Neumann entropy grows linear as a function of time, right? That means that your von Neumann entropy grows as the logarithm of this bond dimension, which means that your bond dimension actually has to go exponentially as a function of time. right? So really, if I would simulate the system to long time, it would become exponentially hard just using this very simple idea. And one fun fact, the motivation of this paper that we did in 2012 was actually to propose an optical lattice experiment where they could measure these entanglement entropies. Because the thing is, of course, if you want to build your famous quantum simulator and you want to simulate something, then you at least better show that you have really a linear growth of this phenomenon entropy, because otherwise I can just simulate it classically. And now one fun fact about this is, of course, it turns out actually people did this experiment. There was a Markus Greiner experiment, of course, for like 8 bosons or something. So they never got to the regime of really cleanly seeing this linear, they saw it a bit. But then, of course, some fun fact is here, if you want to, in an experiment, measure very large entropies at very long times, it gets also hard to measure these entropies experimentally, right? Because you have to measure a lot of, it's like, think about it like some state tomography problem. You have to just get a lot of information out of the state to actually show that you have a large amount of entanglement entropy in the system. So even showing it experimentally is actually a hard problem. And this is just as a word of warning if you hear sort of quantum simulation, because it's hard to simulate. It's not only really the simulation, it's also getting the information out, right? We have already seen, like, also at the poster that you had with like the Pauli strings here. You can also go a step ahead and say, okay, I'm only interested in some particular simple observable in my system, and then I can further exploit that, and then the simulations get actually even easier. Good. Okay, so before showing some cool results, I just want to have a little more now practical comments. So, of course, I have not told you yet, for example, how to compute observables in the system. What I will show you in a minute is, for example, again, staying to this Bose-Hubbard model. I'm going to show some results for the single particle density matrix elements here. Again, this is something which one can immediately compute if I have a state. So in my MPS, I really have a compressed representation of my full quantum state in the system. And now if I want to compute something like B dagger on side 2 and B on side 4, I can write this whole tensor network in this particular form here. And then one can here see that one can simplify this, because here I said already, this is a good orthogonal basis, this is a good orthogonal basis, so actually one doesn't need to explicitly do this contraction here. One can easily show that I can just replace this by a line. So in the end, one has to always compute things like this. All of this can always be done efficiently. For this type of expectation value, always using only a maximum of chi/2 complexity. So this is really not a problem. Okay, the last comment I want to make is what already in the very first lecture I implicitly used this without telling you why it works. That's why I chose to introduce this time evolving block decimation algorithm, because if you have this, if you implement this, I say it's not the most efficient one, but with this you can really do really everything. You can also just compute ground state. And computing ground state works just, again, with imaginary time evolution. It's just a super simple concept. So what if I have these gates? I have this Suzuki-Trotter decomposition. And instead of evolving with I times t, I just look at the evolution operator e to the minus tau h, right? So a non-unitary operator. So if I apply this operator to my initial state, whatever this state may be at time 0, and let's just assume that this state has some overlap with the ground state in the system, well, then I can expand this state psi t equals 0 again in the eigenfunctions of my Hamiltonian. So I use the spectral decomposition of the Hamiltonian. I group my eigenvalues in such a way that the smallest eigenvalue is E0. And then you see simply here that if you just evolve this thing to some long time, you get some distribution of values tau over there. And of course, at very long times, the contribution that belongs to the smallest eigenvalue here, this is the one that's going to be much, much larger than the one for the next smallest one. Right? So if I evolve my system and I keep my state, because this is non-unitary, I have to renormalize my state. But if I do this, if I renormalize my state, I see that in the long time limit, the only state that survives is the coefficient in front here for the ground state. Right? So if you after every gate you apply, after every little time evolution, you renormalize your state, and you evolve it just long enough, you will go into the ground state of the system. And that's the simplest way of just reusing this time evolving block decimation now directly for computing ground states. Yes. Okay, so this is my summary, well, slide of what else is out there. So I really was just scratching the surface of this whole field of tensor network ideas. I just talked about computing ground states with imaginary time evolution. Of course, in practice, that's by far not the most efficient way of doing it. The most efficient way of doing it is to use this DMRG idea, so this density matrix renormalization group that was already introduced in 92. So this was really introduced before it was this understanding that is connected to entanglement also was clear at all. This was only much later there in this early 2000s when this connection was made. But now you can nicely understand this DMRG algorithm in this MPS language, so in the more modern language. And what DMRG is kind of you do a variational update of your MPS. Right? So it's there like you can just go to one particular of the three-dimensional tensors. You can now say, okay, I want to find a new tensor that locally minimizes my energy. And then I find this tensor, I update it, I go to the next one. And then I kind of sweep through my system a few times, and that way I variational go into the ground state of the system. And that's what the DMRG algorithm is. Also, what is very important in a very modern language now, that's why this TBD is not really so commonly used anymore. A more modern way of thinking is also to write the Hamiltonian in a matrix product form, right? So you can do this exactly the same trick. They are just introduced for the states. You can also do with matrices, right? So in this diagrammatic language, the Hamiltonian would now look something like, I have this horizontal indices that tells me kind of like how much correlation does the Hamiltonian induce between sides. And then I have these vertical indices, and then I can have algorithms where I variationally do a time evolution with this Hamiltonian when I apply it to that state. And that's one very common way. One can also produce approximations to matrix product evolution operators and all types of this. Good. I said that in principle with this TBD you can also try doing two-dimensional systems. But the problem is just when I do a two-dimensional system and I write it as a 1D form, I have to do this kind of like snake form. And then, of course, what you will get some long-range terms in the system. And then all that's going to happen is if you simulate this with your fake one-dimensional snake, you will just see that your entanglement is growing super quickly. Right? So in a way, it's possible, but it's just not the most efficient way. It's just because this MPS way it's written, it's like a one-dimensional concept, so it naturally fits both to one-dimensional systems. So of course, people have been introducing sort of 2D and 3D generalizations or ND generalizations of this MPS. They're known as protected entangled pair states. Again, acronyms. It's really not famous in this field. And they have, for a long time, just being kind of in the background, they have not been super useful because the fundamental problem was with these original algorithms of these protected entangled pairs is that the scaling of the update algorithm is just really bad. So it's still like classically efficiently in the sense that you had something like bond dimension to the power of 11 or something, but something to the power of 11 is actually really bad, even if you want to do it in practice. That's why for a long time this was not used too much. Now this is actually quite useful for if you use infinite systems. There have been some very nice results. Then there are things like tensor network trees. This is something I honestly don't know too much about. There's something called multi-scale entanglement renormalization answers, or MERA. So the idea is fundamentally that sort of one has sort of some physical indices at one point, and then one coarse grains the system into a virtual dimension, and sort of trying to distribute the entanglement in the system into this dimension. Here's something I want to talk a little bit now on the next few slides when I show some recent results. One can also do the same now for an open system dynamics, right? Again, same as the Hamiltonian, if I have a full density matrix of my system, I can also write it in this matrix product form. This is known as matrix product density operator. And last comment I want to make is something which is also very nice. You can also do translational invariance in the system. Right? I mean, as I mentioned before a little bit, there's of course some conservation laws which one can exploit. And of course, one can always exploit some kind of symmetries of your problem. And the easiest one conceptually is if you have like nearest neighbor type Hamiltonians. So they only act on two sides, and you have a translational invariance over two sides. So then actually it turns out you can think about your MPS as an infinite MPS, where you just have two of these three-dimensional tensors, one you call A and one you call B, And you just think about repeating them up to infinity. And then instead of evolving sort of a large system, you can just evolve really 2 of those tensors. Or if you have something that breaks the translation invariance over larger systems, you just need a bit of a larger system. But this has been very, very useful in many different works. Good. I mean, there are many openly available review articles. I still like the one by Uli Scholwerk best. It's a bit old now, from 2011 already, but it fundamentally has all of the concepts in there, and I think it's, because it's not complete anymore, there are some newer ones, but this is still very nice, so that's the one I would recommend as a starting point still. Good. So let me spend now the last time to just introduce this concept. And the main message I really want to get across is it's not a big deal to simulate larger systems quantum mechanically, even fully exactly, because it's not the system size that matters, but it's the entanglement that matters. So now I wanted to show you some results where we applied in the past this MPS technique, and also some very recent results, just to motivate a bit what the open problems are. But first, I thought I would go back to this question with the Gross-Petersky equation and the validity of the Gross-Petersky equation. So I was going back to the Bose-Hubbard model and showed some results there. So first of all, this is, I mean, what you find if you do these ground state calculations in the Bose-Hubbard model. Here I show now 2 results of the single particle density matrices. In this model, I have again my hopping and I have my interaction strengths. And on the left-hand side, I show very strongly interacting systems. So this is in this mod insulator regime. And there, of course, you see that here you have, this is for all of the elements in my chain. So this is 48 sides. So you see the diagonal elements of this are, of course, just the local density. So this is a system where I have 1 particle sitting per side. And I have some small boundary effects here on the edge there. But then I see that if I go out in space, like the correlations between the boson, it just decays exponentially. Right? So that's the signature of the mod insulating phase. On the other hand, if I go to like a very weak interaction strength, I can now also compute this density matrix, and I see I get these sort of large off-diagonal elements in the system. Now, the important thing you see here, if you are used to kind of 3D systems and Gross-Petersky equation physics, then usually your Bose-Einstein condensate or your superfluid, you just have it. It's characterized by this off-diagonal long-range order, which means if you do your mean field approximation and you go into this superfluid phase, you would actually expect that you see sort of the off-diagonal elements to be like at a constant finite value. Because what this means is that it implies that you have sort of one macroscopic occupation of one particular mode in your system. Now you see this is not what happens in 1D, because, okay, this is kind of just a plot for show. More scientifically, I would just plot this as a function of the distance, but one would see, of course, that here I don't get a constant value at long distances, but I get actually this algebraic decay. And this is really the peculiarity of 1D, that there's this no off-diagonal long-range order, but instead I get algebraic decay. And now, of course, after Thierry lectures, you know exactly why this is the case, because there you can describe it by the Lutzinger liquid. And exactly if I would now take this and I would take this fit of how it decays, then I could extract the K parameter, and then I could, again, use this field theory just to compute a lot of more things that I like. Here, exactly at the superfluid transition point, you would find something like, according to my definition, of 1/2, but there are some different definitions. Okay, so that's one thing. Again, if you would do a mean field ansatz, the Gross-Petersky, you would find this long-range, this real true long-range order, and this would not be the true thing that happens in 1D. Also, if you compute, for example, the transition point, I mean, people have really tried to do this very precisely using these MPS methods. So, of course, I mean, the change of this behavior here and here is, of course, because you have here a quantum phase transition. That's all at like 0 temperature. It's really just ground state physics. And if you do a mean field calculation, this is simple. One can do this analytically. One finds something like 11.6. But then in reality, you actually, so this is the ratio of the interaction strength to the hopping. So you make this larger, then you go into this mod phase. If you make this smaller, then you go into this superfluid phase. And in reality, it's something like 2.9. Right? So there's really quantitatively, this is quite off. Okay, but going back, because I mean, this is all I want to talk about non-equilibrium. So this is, I just re-put the slide from the first lecture that I had when I had just this, I had introduced the Gross-Petersky equation, which is the mean field theory for this problem, and I simulated it in 1D. And oops, and just to show the movie again, I had this situation that when I kick the system here, you see that it goes over, and I kick it with a certain strength, and this was called the dynamical instability, and that's something that really came out from this mean field theory. So there have been some nice experiments about this already in 2007 in the group of Wolfgang Ketterle. So what they did in this experiment is that they really prepared the superfluid state. They had this optical lattice set up. And then just they prepared the superfluid, and then at one point they start to move the optical lattice in one direction, which is completely equivalent of saying, okay, you take your superfluid and you just displace it in momentum space, and then you just see if the superfluid stays stable or if it decays. The way that they do is, of course, then they turn off all the optical traps, they do the time of flight, and they measure how many particles are in this one condensate mode. And they just check, depending on how strong the interactions are in the system, and depending on how much they kick the system, is this Bose-Einstein condensate, this superfluid, is it going to survive in the system? And then one can get this kind of like dynamical phase diagrams here. So here on the x-axis, there's the interaction strength. So this is controlled by how deep you make this optical lattice, or by tuning some scattering lengths between the atoms. And then on the y-axis, there is sort of the amount of how much they kick the system. It's exactly the same number that I had on the previous slide, where I had this Ka parameter, which was the kick parameter. And then they determined the point at which point the superfluid is really destroyed. Right? So over here it's destroyed, and here it remains completely stable. And that's for like a 3D optical lattice. So this is really the full 3D thing. They just kick it in one direction and check if it survives. And this beautifully matches like the Gross-Petersky theory. So the mean field theory is just this line, and the experimental points were exactly doing that. But then they can also do the same experiment really in a 1D setup, just making it like lattice very deep in two other directions. And then you see that this sharp behavior from this superfluid stable flow to this decay is just completely disappearing. Instead, what this is here, this is really a plot of the condensate fraction. So this is the amount of particles that are in this one mode that tells you how superfluid your system is. And this is just as a function of how strong you kick the system. And then you kick it a little bit more, and then this is at like a fixed time. And then at a fixed time, you see that this condensate fraction is going to smoothly going down. So there's no sharp up and down like in the 3D case. And this is something what one can easily do with this MPS things. So here, this is, for example, a calculation for where it takes an infinite system using this idea of this translational invariant MPS. I show here on the left side, this is the momentum distribution. So this is already after I apply a kick operator to the system. I can prepare my superfluid state. It has a huge occupation in one particular mode. This is this peak here. This is one momentum mode. But now I shifted this momentum mode from 0 to 0.4. Just exactly in the same as in this GP simulation that I had done before. And now here I see this is fully exact 1D calculation. I see that my condensate gets destroyed because particles go out of this condensate mode and they go to something much broader at long time. So this is a different TJ5 or TJ10. And then one can really also, using MPS, one can really reproduce this smooth behavior, right? So here's interaction strength U. This is U over J. It's 1. So if I kick the system just a little bit, my condensate stays quite stable. Of course, if I go to longer and longer times, I will still see that this condensate fraction that I plot here is going to decay a little bit. But then I kick it a bit more, it decays a bit more, and so on, and it goes down. And then one can make really an exact type of version of this dynamical phase diagram using this MPS. So here is just the condensate fraction. It's the decay of the condensate fraction plotted at a fixed time, sort of 10 tunneling times here. So if this number is going to go to 1, it means all of your condensate is lost. If it's 0, it means your condensate is stable. And so you see you have a small region where it's relatively stable, but then you have this smooth crossover to a behavior where your condensate gets lost. And this does definitely not fit the mean field line, which would predict the sharp behavior, which is over there. And this was published in this work. It's a very nice paper because it's the first paper I ever published. That's why I show it. So now I want to show you the last paper I ever published. Okay, so now I have a few minutes left. and I want to just motivate sort of some very recent topic that I find very interesting in this field. And that's now just applying this all to like a sort of open system evolution, right? So now again, I go from evolving, instead of evolving a Schrödinger equation, I want to go to a master equation. And fundamentally, there are two ways that I can do this. I both introduced them in this lecture. Sort of the one was, the last thing I introduced was this matrix product density operator, right? So this is just using this trick of this MPS just applied to a density matrix. So instead of having my, my virtual matrices with the elements being little state vectors, I can write down these matrices with elements being little density matrices. And then, of course, I can do the same type of tricks I did for an MPS. I can do singular value decompositions. From that, I can get some eigenvalues of my reduced super operator density matrix. And they're going to give me some entanglement entropy. I can do this, and this is called the operator entanglement, was introduced by Zanardi in 2001. And they call it entanglement, but it's important to say it's actually not really entanglement. I mean, in a quantum information sense, it doesn't mean entanglement at all. It just means if you vectorize your density matrix, you do an SVD, so you have effective super operator eigenvalues of your subsystem, and they're going to give you some type of entropy. And but one does not need to care about this, because the important thing for this MPS business is, of course, you use just this entropy as a number to summarize how easy or hard it is to do a simulation in practice. So even if it does not mean entanglement, and even if people call it still entanglement, it's just a pragmatic, important number to tell you how efficiently you can compress a density matrix if you want to write an MPS. And that's the one thing. So here now the important quantity to look at would be this operator entanglement. If I look at some dynamics, I quench my system, but I have some noise processes. The question is, how does this operator entanglement go? It's going to tell me how efficiently can I simulate it with these matrix product ideas. The other thing is what I introduced in the second lecture was just I can do this quantum trajectory approach, right? I showed you that every type of evolution with a Lindblad master equation, I can just unravel the evolution. I can say I have an approximation to my density matrix, and this is just going to be some statistical mixture of some states with some certain weights. And then we arrived at this sort of stochastic evolution equation for the states. And I can do this with MPS, of course, too. So I can just take each of these trajectories. I write each of the trajectories as this matrix product state that I have just introduced. And now the question, of course, is if I can simulate some dynamics in an open system, it's now connected to the question, so how does the entanglement in these trajectories go as a function of time? So one can define kind of like an averaged entanglement entropy. We call it just a trajectory entanglement. There are other words out there. And then this is the quantity that should be sort of an indicator about how difficult things are to simulate on your classical computer. And so here, though, this was just the latest result that we had there, which we found kind of surprising. So this is just, I show you some results for a standard XXC model. We take just a typical Lindblad master equation. We look at different type of noise processes. Here we have something like which is spontaneous decay and spontaneous absorption of your two-level system. It's maybe a bit of an artificial dissipator, but this is just, the thing is just if you have like a dynamics with a spin chain, you just add some decay. Of course, your long-time physics gets extremely boring because you're just removing excitations and you go to a trivial state at very long times. So to keep it interesting, we also just incoherently pump excitations in the system. And that's the results I showed. Here we also have some results on dephasing, if one puts like a sigma C jump operator in there. And then what I found fundamentally interesting is that if you look at this, so sorry, the contrast is again pretty low. So I show here that the time evolution, we start initially in a highly excited state, in a nil state in this case. And we look at the time evolution of this operator entanglement. So this quantity tells me if I write my state as a matrix product of this matrix product density operator, how good can I do this? And one finds a typical behavior that sort of this entropy is going up for a maximum value. So this is kind of this linear growth, which is really quantum mechanical and hard. But then your dissipation starts to kick in, and then this operator entanglement goes down, and here it goes to a value that is 0. Right? Which tells you if you simulate this thing with a matrix product density operator, you go to long times, then you have a trivial density matrix because all these matrices, they're going to have a dimension, bond dimension that's going to be 1. Right? So it goes really to a trivial state that I can easily write down as a density matrix. However, if I just apply the standard idea of this quantum trajectory approach as I introduced it earlier, you will find this. You will find that this entanglement in the small gamma case actually keeps growing. And even for large dissipation, if I go to gamma 0.7, it goes to a constant value here. Right? It means that I have, if I want to simulate some dynamics back here, if I use these trajectories, it's actually a quite dumb idea because I have a trivial density matrix in the long time limit, but here I just write it down as a statistical mixture of entangled states. And if I keep going, the entanglement in these states is actually going to go growing. Right, so this is telling you that really this standard type of unraveling of the master equation is really sometimes not a good idea. It can sometimes even be more efficient to simulate the whole density matrix because this operator entanglement can be much smaller than this trajectory entanglement. But of course, it also tells you that this is not ideal, this trajectory entanglement, because of course, what I had not told yet is the unraveling that I introduced in this lecture is of course not a unique unraveling, but there are like many different ways. I mean, because this is a density matrix, I can decompose it in many different ways, and one can also define many different kind of stochastic evolution algorithms that give rise to the same master equation dynamics, but they just unravel it in different types of trajectories. And that's the motivation of the most recent research project, and maybe some of you have seen Ruben's poster, is to find ways to kind of, in an optimal way, reduce the entanglement of the trajectories to make it better applicable with these quantum trajectory methods with matrix product states. Okay, so just one other result, just to also show you that there are some really interesting, still not understood many-body dynamics going on. So this is one now, some other very recent work where we had kind of like a very similar system, actually almost the same setup. And there we found something interesting. So this was a work where we exclusively looked at the evolution of this operator entanglement growth. So, and the model that we looked at was this XXC chain again, and then, but specifically we looked at some master equation where we had some dephasing in the system. Right, so some Lindblad jump operator that has the form of the Pauli sigma C matrix in this case. And then usually one would expect, again, as I showed you before, there's some papers of this, there was again this initial rise of this operator entanglement, and then typically one finds this peak, and then typically one finds it goes down to 0 or down to some constant. But then we just try to simulate this thing, and we find this surprising thing that actually this operator entanglement goes up, it goes down, and then it starts to grow again very slowly. First believing this is some numerical mistake, but this is actually a real thing. And so this is also, note, this is written on this logarithmic x-axis, so this is really a very long-time evolution here. And what's furthermore interesting, we found that this long-time growth seems to be kind of universal. It goes like the logarithm of the time divided by 4 plus some constant, where this constant really only depends on how high this peak is in the beginning. And what we found, essentially, I cannot really tell the whole story here, but we found that this is really a consequence because in this type of model, you have really a strong symmetry, so you have a strong conservation law. Because if you think about the total magnetization of the system, and you start in a nil state in an infinite system, your initial magnetization is going to be fixed. And also these Lindblad operators themselves, they're going to preserve the magnetization. And then if you have type of this behavior, you find that if you go to long times, if you think about how your density matrix is going to look like, it's going to have this block diagonal form because it has these blocks of different symmetry sectors with different magnetizations to the left or the right of the chain. And what we found is that one can find sort of some classical evolution equation for how these blocks to distribute in a density matrix. And so even this in a case when all the elements, if you go to a large dissipation limit, one can write down a perturbation theory. So then even all the off-diagonal elements of the density matrix, they go away. You have a fully diagonal density matrix, but it still has these blocks, and there's a distribution of these blocks, and this distribution of these blocks keeps changing according to some classical process. And from this, we could analytically derive this logarithm divided by 4 behavior at long times. And again, in the spirit of this class, sort of thinking about dynamics in terms of complexity, I like this very much because here you have now an example where this entropy goes logarithmically. So here we had no problem to simulate this to a very long time because if the entropy goes logarithmically, then your bond dimension this chi parameter only has to grow linear as a function of time, and that's classically really easily doable. And the reason why this is the case is because we found here there's really a classical process behind that that's governing this. And that's why it's logarithmic, because that's what the classical process can give you. And that was published in this paper over there. Yeah. This is the smallest one. This is J/4. Then, sorry, you cannot see this. There's one curve that goes up here. That's for J/2, and then J2, and then, of course, if you make it very large, the dephasing, then you kill any type of this initial coherent dynamics. You go immediately just to this dissipative limit where you have this log growth. But here you have some, I mean, really what this tells you, if you want to simulate this on a computer, the hard part is to get over this initial peak. And then once you're there, you go down, and then you have still some correlation build-up at long times, but it's kind of classical, so it goes only logarithmically. Yeah, the explanation is like if you do a perturbation theory in the large dissipation limit, and then, so what you can look at, if you look at this quantity, the operator entanglement, if you look at it for like in a situation where you have a strong conservation law, you see that it actually has two contributions. The one comes from the fact that you have like a block diagonal form of your density matrix where you have a distribution of the blocks. And that's called the number resolved entropy. And then on top of this, you have in each block, you have some off-diagonal elements. And this is called that's called the symmetry resolved entanglement. And the other one is called the number entropy. And what we see is that like this symmetry resolved entanglement entropy, that one goes to 0 away in this limit. But you still have this number entropy, which simply comes from the fact that you have a classical distribution of symmetry blocks. So I think it's very hard to understand without showing the formulas, but what do you, the non-Ham? Yeah, but no. Yes, no, but I mean the thing that wants to increase it is of course the Hamiltonian. You start with a state which is not an eigenstate. This is a Nail state. It's a highly excited state. So if you have this Hamiltonian, it's going to start to introduce some real entanglement in the system. And that is one contribution to your operator entanglement entropy. And this is, the Hamiltonian gives rise to this initial linear growth that you unfortunately cannot see here. There's a line that goes up linear here, up to a certain point. And then at that point, then like the dephasing part starts to take over, and it starts to destroy the correlations that you have introduced by your Hamiltonian. And this one makes it go down. But then at very long times, you have again kind of a classical process coming from this number entropy part of the operator entanglement. And this is going to give rise to this long-term growth. So if you have no dissipation at all, right, this is just going to go linear. And it's going to be, just like in this Bose-Hubbard example, it's going to be hard to simulate. Good. That's the end. So I thought last slide I just give a full recap of everything that I tried to get across. So again, the spirit was to discuss some kind of numerical techniques with the idea that you try to simulate some physics to actually learn something about the dynamics in the system. So we did some very fundamental things, discussing how to write numbers on your computer and just some basic linear algebra, exact diagonalization. Just some general Swiss Army knife tool to do any type of evolution. So there's these Runge-Kutta methods and these Krylov space type methods, which Krylov space is particularly important because you typically want to have Hamiltonians that are very sparse, and then this is a method that exploits this sparseness quite efficiently. And sort of we had all of this discussion about like linear physics, but of course, not all problems are linear. If you make some mean field approximation, for example, Gross-Petrovsky, you can really drastically reduce the space of your system. Right? It's really like in an MPS. MPS, you make this bond dimension huge. You have all of the space of all of the states. But if you send this bond dimension to 1, you just drastically reduce the space that you consider. But then what can happen is that your equations become nonlinear, like in the Gross-Petrovsky equations. And no problem to solve this numerically, but of course you make a strong approximation because you neglect any type of entanglement in the system. So this is really a limit of a matrix product state where you set this bond dimension to 0. Discussed a bit like how to do open systems, so either linearizing a full density matrix or doing this quantum trajectory evolution approach. Like also discussed how to construct these Liouvillean matrices, for example. And then in the first 2 lectures, we were really saying in this exact regime. So really, if you want to do everything except if you want to go with your full state, keep all of the information, even if you don't need it, then you can do something like 30 qubits on just a classical computer. But of course, the information in a state is just overkill. Yeah? So it's much more better to actually find ways to compress the information that you actually need. Here, I introduced this matrix product states, which is kind of a compressed way of writing down a state vector, still keeping a full state vector representation. Okay, so one important takeaway message, it's really not the system size that's important, right? So if somebody tells you in a quantum computer you just need to add 1 more qubit because then you gain exponentially, this is not true, because the resource is not the system size, the resource is really how much entanglement you actually introduce in the system. So that's an important takeaway message. And there are many interesting, still open questions, even in 1D, just thinking about entanglement and how it grows as a function of time in general dissipative systems. Okay, and that's it.